Okay, so we're now on to Unit 6. This is Unit 6, Day 1A. We're talking about vectors. So I'm not sure if you did, I assume you did vectors in geometry, but I'm going to try to basically assume that you didn't. And so if you have some previous knowledge, that's awesome. If not, then hopefully this covers it all for you. So I can identify the magnitude and direction of a given vector and express it in different forms. So that's my learning target for the day. So first off, a vector, it sounds like a real crazy scientific word. It's really not. It's just basically we use arrows to represent them on paper. So a vector is a quantity that has magnitude and direction. Okay, now if it doesn't have that, if it just has magnitude but no direction, then that's called a scalar. That's just like a number, but when you have direction, then that's what makes it a vector. So every vector, when we draw it, has to have an initial point, which is a starting point, and it has to have a terminal point, which is the end point. I think when you draw an arrow, you put the pen down, that's your initial point, you draw the arrow at the end, you put an arrow in the end, that's the terminal point. Now it doesn't actually keep going. So I know when we were graphing, like when you had linear equations in Algebra 1, you had to put an arrow on the end of it. And when we, anything we graph, you're supposed to put an arrow on the end of it to show that it goes on forever. These actually stop. Now we have an arrow saying this is the direction, but it's length. We use length to describe the magnitude also at times. So typically the longer it is, the more magnitude it has, especially if you're comparing two to each other and you're drawing them both on the same diagram. The distance from the starting point to the ending point is called the magnitude. So the direction corresponds to the direction the arrow is pointing. These vectors can be represented by a coordinate pair in the coordinate plane. This is called component form. So we'll give the components, and what that is, we'll explain in a second here, but just has an x and y component, and that's your x and y coordinate. Now, equivalent vectors, they don't have to be drawn in the exact same place, but equivalent vectors have the same magnitude and same direction. Opposite vectors will have the same magnitude but opposite directions. Okay, so if you have two vectors, they're the exact same magnitude, same direction, but they're just kind of floating around, one's here, another one's over here. Those are equivalent because it's the same magnitude, it's the same length. I try to make them go the same direction, the same angle there. So those would be equivalent. If I draw something like that, would not be equivalent to those two because it's longer, so it has more magnitude. And if you think about weight, that means it's heavier. We're talking about speed, then it has a faster, it's going a lot faster than the other ones. So down below here, you look at this and you think, well, that's just an angle that we've been dealing with for the last couple of units. It has an angle, it has a direction, has a length, and that's what it is. It's actually a vector too, so it's nothing really new here. Now the magnitude on this would be the length, which is 65. The direction on this, typically the direction we say is from going straight to the right, so this would be, it's 50 degrees down, but we'd also want to say going this way. So this would be 310 degrees because it's 50 degrees short of a full circle. We could say from the true bearings, from straight north, we could do some of that, but we always typically say from straight to the right, just like we have been doing. The initial point is at 0, 0, and the terminal point on this one, we got to do a little bit of work. If I want to find this point, to go 65 units, how far to the right, how far down do I have to go? So I think if this is 50 degrees here, to find how far over, that's my cosine. So if I do cosine of 50 is going to equal x over 65, so I'm going to bring the 65 over here. While we're doing this, we're doing vectors, cosine will always help you find the x. Just kind of keep that in mind, it's a shortcut. Cosine will help you find the x. I'm going to do the exact same thing to find the y. If you look, sine of 50 is opposite over hypotenuse, that's y over 65, bring the 65 over, it's just kind of a shortcut. The magnitude times the sine of the angle will give you the y. The magnitude times the cosine of the angle gives you the x. So I type these in the calculator, I get 41.8 and negative 49.8. It's a negative because it's down. So if you type this into the calculator, you have to figure out the y is negative. Now, one shortcut on this, you could try this too. If you do 310, if I type in 65 cosine 310, it still gives me the 41.8. So it's the same thing as this. So these would be the same. But if you type in 65 sine of 310, the calculator knows that 310 is down here. It gives you a negative. It'll give you a negative 49.8. So if you give me the degree counterclockwise from straight to the right, the calculator will figure that out for you. Now, in component form, since this started at 0 and this goes there, how far did it move to the right? Well, it moved 41.8, so 41.8 is the component form. It just happens to be the exact same as this, but that's because it started at 0. If that was not the case, if it started at 1, 1, then this would be 40.8, and that'd be negative 48.8, because you'd have to subtract these, but since it started at 0, 0, that's kind of the easiest case. Just some things here. If v is represented by the arrow from this point to that point, from this point to that point, then its magnitude would be this, which is just the distance formula. And we put these lines around it. That's not absolute value, that means magnitude. Okay, so that's our magnitude. Now, if you have the vector in component form already has taken, to find the a, you take x2 minus x1 to find your a. So you don't need to do that. It would just be a squared. And then y2 minus y1 would be your b. So if it's already in component form, you've already done that work. So it's just a squared plus b squared, and the square root is the magnitude. So again, this is not absolute value. This is magnitude, just how long it is. And we're not going to do a negative magnitude. So it's going in the, because if it was a negative, that means it's going the other direction. We'd be going that way then. So we'd give it a different angle, saying it's going backwards. And resolving the components here. So kind of like I did back here, when I knew the magnitude and the angle, how do I find the components? Say the x is v cosine theta, the y is v sine theta. The magnitude of v, the magnitude of v. So it's like I did over here, 65 cosine theta, 65 sine theta. And that's breaking down into its components. Okay, so let's flip this over. We're just going to do some changing. This guy here. I think if I go down the polar form is where you give the magnitude and direction. So you give the magnitude, comma, and then the theta. So in this case, this was 65 and 3, and I just put the angle there. This is 310 degrees. So 65, comma, angle 310 degrees. Now if I want to go to component form, I did that on the front side already. The component form was 41.8, comma, negative 49.8. Again, that was using the magnitude of v cosine theta, magnitude of v sine theta. And that gives me these components. I'll get to bearing in a second. So on this guy, when I want to find this, I don't have my component. I can't do my component form here. I don't have the magnitude or the direction, so I have to do a little bit of work myself. So I'll find the magnitude first. So from 1, 2 to 5, negative 6, I think if I plot that, so 1, 2 to 5, 2, 3, negative 6. To get from 1 over to 5, that was 4 units, so 5 minus 1 is 4. And then going down to get from 2 to negative 6, that's a drop of 8 units. So you could think 2 minus negative 6 is 8. So if I want to find the magnitude, it's just find the distance, think hypotenuse of this guy, so 4 squared plus 8 squared. This guy, so 4 squared is 16, so 16 plus 64, that would be 80, and then square root that, so that would be, let's see here, so I could take a, so it'd be a 4, so 4 radical 5 is my magnitude, and then my angle in this one, if I want to find this angle in here, if I want to find this angle, I got to use tangent. So inverse tangent And that would be, there's a couple ways of doing this. So if I do this angle right here, so second tangent, opposite is 8, adjacent is 4, I get 63 for that angle right there. But what I really need is I need this angle to describe it in polar form. So kind of a faster way of doing that, this is down 8. So you could really say inverse tangent, it's down 8. So it'd be a negative 8 divided by 4. And that tells me it's down. It's negative 63, because when it says 63, that's almost implying that it opened up, and it didn't. So if we put the actual negative and positive values in on this, that does help a bit on this. So if it's negative 63.43, well, that's really 296.6. So whichever route you want to take, if you know that this is 63 in here, you can figure out yourself what the rest is. But now component form, I've already got done here, because component form is how far over to go and how far down to go. So from the initial point to the terminal point, it went right 4 units. It went down 8 units. Okay, so that's the component form of it. Now bearing form, probably going to be easier to use to go from polar to bearing. But if you remember, bearing has to do with, we got to give it a magnitude. So this is still 65, this is still 4 radical 5. But now bearing is from straight north. So if this was 310 degrees around this way, we want to know how for bearing we go this way. How far that way? So it was 50 degrees here. So if this is 50 degrees here, you need to add 90 to it. So it'd be 140. So the bearing is 140 degrees from straight north. Okay, and this one here, we said this was, what, 63 or so degrees this way, so it'd be 90 plus that 63. So the bearing would be 153.4 degrees from north. Now the bottom thing here, this is kind of confusing. We'll get more into it because this kind of applies to future unit or future day. But it talks about the unit vector. So let I be the unit vector 1, 0, and j, which means go right 1. J be the unit vector 0, 1, which means go up 1. So there's a standard unit vectors. Well, if I want to rewrite, and this is more going from component form, be the easiest one, you're basically saying how many I units, how many 1 units to the right do I have to go? So this one, if this is 41.8 to the right, that means I need to take 41.8 times I. And then this is down 49.8, I need to subtract, I need to take away 49.8 times the j vector, which means down 1. Or I'm sorry, up 1. So if I'm subtracting, that means down. Basically what you're doing is putting I and j after the x and y. But there is a reason for it. So if this was 4, -8 component form, this would be, you're going to take 4 times I being the vector that says go right 1. So I'm going to do that 4 times. So 4 right 1s. And then I'm going to subtract, I'm going to take away 8 times the up unit. Well, if I'm subtracting, that means down. So down 8, you kind of get the idea, it's down. So it'll be right 4, down 8 on the way. So yeah, we'll get more into that, but if you see that on the homework, that's all that means. It's a different form for describing a vector, but they all of these are just different ways of describing the same kind of vectors. So hopefully that doesn't get too confusing. Honestly, I think linear combinations and component form is like the easiest ones to use because we're so used to it. The bearing form, we're kind of just going over it so you know what it is. It's not really going to be a big thing that we're going to use a lot. So that's kind of nice because it just throws everything off since we're using it from a different starting point of the angle. But yeah, let me know if you have any questions.